The oxygen sensor and Lambda sensor is an electronic device that measures oxygen exhaust gases exiting the engine. This is located in the exhaust system and provides real data for vehicle engine control units, which is used to adjust air fuel mixture for optimal performance and combustion. Primary goal of this sensor is to maintain approximately 14.7 parts air to 1 part fuel for gasoline engines to maximize fuel efficiency and emissions. The oxygen sensor uses a solid chemical electrolyte made of porous zirconium dioxide and two platinum electrodes to create a potential difference between the electrodes that is directly proportional to the amount of oxygen in the exhaust that passes over the sensor. This sensor is activated at roughly 600 degrees Fahrenheit. When the oxygen level in the exhaust decreases, the voltage level of the sensor increases. When the oxygen level in the exhaust increases, the voltage level of the sensor decreases. The sensor range is 0 to 1 volt, and the stoichiometric air-fuel ratio of 14.7 to 1 will create a voltage of 450 millivolts. Observing the scan tool in real-time data, you can see that the system toggles from rich to lean and averages about 450 millivolts. Not all oxygen sensors are created equally, or do they work the same. In today's systems, there are basically three groups. We discussed zirconia earlier, which is voltage changing. The titania sensor is a veritable resistance sensor, and what is most common on newer cars today, the wideband Lambda or air fuel ratio sensor, which is current changing. While the zirconia sensor works, as explained earlier, on voltage changes, the titania sensor works to a different way to accomplish the same goal, to maintain the average stoichiometric air-fuel ratio. The titania oxygen sensor is a veritable resistance sensor that changes its resistance value with the amount of oxygen present in the exhaust. It does not use a comparison sample of atmospheric air. Instead, it is supplied with a reference voltage from the computer, usually 1 or 5 volts, and varies its resistance in proportion to the amount of oxygen present in the exhaust, thus changing the amount of voltage after the fixed resistor in the computer. One thing to note is the titania sensor uses a 14 millimeter thread that is not interchangeable with the zirconia sensor. A wideband oxygen sensor, sometimes called a Lambda or air-fuel ratio sensor, changes the current flow from and to the PCM on the O2 sensor circuit. A rich mixture will cause current to flow to the sensor at a rate from 0 to 2 milliamps. 2 milliamps indicating about a 12 to 1 air-fuel ratio, or a very rich mixture. A lean mixture will cause current to flow to the PCM at a rate of 0 to 1.5 milliamps, with 1.5 milliamps representing a mixture of about 22 parts air to 1 part fuel. Air-fuel ratio, which is very lean. When the air-fuel ratio is at stoichiometric, there is no current flow in either direction. In this screen, you can see the top left corner is a heated oxygen sensor, and it's fluctuating from 0.84 millivolts to zero point zero 0.02 volts, making an average of around 450 millivolts. On the top right, you can see a heated oxygen sensor 2. This is monitoring the catalytic converter's efficiency. The bottom left, short-term fuel trim, is real-time adjustments adding or subtracting fuel. And bottom right, long-term fuel trim, which is adding or subtracting fuel over a length of time. Hopefully, you'll take some time going into the scan tool and looking at oxygen sensor values. Learning and understanding these values can be an effective tool in diagnosing fuel-related issues. Hopefully, this last section can give you some diagnostic helpful hints. This particular slide shows a normal operation. This one is running too rich. This oxygen sensor too lean. This one isn't fluctuating properly. This sensor has silicone contaminants. This one has coolant contamination. This one has carbon buildup. And this one has lead in the fuel.